Good. Okay. So there's still people coming in, but I think we'll start. It's my great pleasure to welcome today's distinguished lecture series lecturer. It's my or our colleague Mischa Bonn from Max Planck Institute for Polymer Research in Mainz. We invited Mischa a while ago because we were actually interested in him visiting our institute. A lot of what he does might have just as well happened at our institute. A lot of high-end optics and laser spectroscopy that is done. I would say the only disadvantage in the Max Planck Society is that we're not all on one campus. You don't get to interact with each other. But so I hope that this gets a kickstart to have more exchange between Erlangen and Mainz. So let me introduce Mischa to you as it's usually done. So Mischa did his undergraduate work in physical chemistry at the University of Amsterdam. Then he got his PhD in a joint effort between University of Eindhoven and Amolf in Amsterdam. And then he already came to Germany to do a postdoc at the Max Planck Institute, or let's say the Fritz Haber Institute of the Max Planck Society in Berlin. And during that time, he also spent some time with Tony Heinz in Colombia at that time. Then he went back to the Netherlands and started his career as a professor, as an assistant professor at the University of Leiden. And there he became associate professor. And so he has lots of affiliations that have overlapped with each other. It's a little interesting, but he was also an extraordinary professor at the University of Amsterdam, which he keeps that position till today. And then in 2011, he moved to the Max Planck Institute in Mainz, and he's also an honorary professor at the University of Mainz. So Mischa is very well known for his ultrafast spectroscopy, laser spectroscopy, and looking at vibrational degrees of freedom in molecules, in particular in water, which is the topic that he's particularly well known for. But he has chosen to talk to us about terahertz optics with graphene. So I would say this is a newer topic, and we're very much looking forward to hear what you're doing there. The floor is yours, Mischa.
Thank you very much, Fahid. It's a pleasure and an honor to be able to tell you some of the work we've been doing on graphene with terahertz radiation, and it's a little peculiar to be doing it from my own home. And for those of you who are curious, yes, I am wearing pants. So I put on a jacket for you, but I am also wearing pants. So let me move forward. So it's important that I acknowledge the people in my group who started this effort, Dmitry Turchinovich, who's now a professor in Bielefeld, long-standing collaboration with the ICFO, and we did experiments with Micha Gensch at the Helmholtz in Dresden, and that's a big part of this work. So a lot of credit goes to these people here. So let me start by telling you a little bit about graphene. So I think you know what it looks like, right? It's this hexagonal arrangement of carbon atoms. Graphene has a very interesting and peculiar band structure. It's this conical band structure with a density of states that is vanishing at this direct point here. This means that it absorbs light with equal transition, probably with equal intensity across the whole spectrum. And it also means that because there's no quadratic dispersion of the bands, which you normally have, which determine the mass of the carriers, the carrier mobility theoretically is actually not so far from the light velocity. So it's the light velocity divided by 300. So it's a very unique material in many ways. Now, there have been many, and there have been developed many applications in sensors, in detectors, in transistors as photocatalysts. But a lot of that work has been developed by trial and error and not by a fundamental understanding. And the nicest example of that is this perspective on graphene, which is called beyond guano doped graphene. And now you may think that, guano is some exotic element that you have not heard about before, possibly. Well, it's not, because if you look up guano, guano is the accumulated excrement of seabirds and bats. So this is actually literally crap. And that is actually the title of a paper that was published in ACS Nano this year. Will any crap we put into graphene increase its electrocatalytic effect? And so this is, I think, highlights the limitations of our understanding of fundamental processes in graphene. And so this is what we set out to do, is can we understand better what is happening in graphene? And so the goal of the work that we've been doing is to use the terahertz waves, and I'll show you why those are useful, to not only characterize, but also control and utilize the rather unique optoelectronic properties of graphene. So before I continue with the sort of the real talk, I'd like to ask you that if there's anything that you can't follow, or if I go too quickly, then please just interrupt me. That is, I think, much better than that you leave me talking to my screen. So just
so maybe as a note, I'm not sure if everyone is allowed to, or if it's possible for everyone to use their microphones, but there is a chat line, and so if you have questions, then put your question through the chat line, and I'll make sure that Mischa gets.
Yeah, so please, Fahid, if you could keep track of that, that'd be great. And then just feel free to interrupt me at any point in time. All right, so very quickly, terahertz is this frequency range here. So it's obviously centered around 1 terahertz. And it's, interestingly enough, the place where high-speed electronics meet very long wavelength photonics. So here's the spectrum, and you see it's sort of also been called far infrared. And with electronics, you can go, into the gigahertz and terahertz regime, but you need high-level electronics. So it's an interesting frequency range. Now, graphene, if you put it on a substrate, and if you're going to make a device, you're not going to have like freestanding graphene. It's going to be on a substrate. And if you put it on a substrate, you actually shift the Fermi level up or down, depending on the nature of the substrate, and you typically get a shift of the Fermi level by about 200 millivolts, which corresponds to a density of carriers of about 10 to the 12th per square centimeter. So this is important to keep in mind, that graphene, it's a semi-metal, but it is actually conducting when you put it on a normal substrate, because it gets doped. And so what we do is we try to measure the conductivity of the graphene. And so the conceptually, it's very simple. If you want to measure the resistivity or the conductivity of a material, you take your multimeter, you apply contacts, and then you apply an electric field using those contacts, and you do that over seconds, and then you read off the resistivity. Now we're going to do essentially the same, but in a much more complicated way. And the idea is to use terahertz spectroscopy, which is essentially a single cycle, a single oscillation of the electromagnetic field that can propagate freely through space. And then the field is only on for about a picosecond. But it's essentially the same thing here. And it has a couple of advantages in terms of measuring conductivity, because it's ultra fast, right? The field is only on for a picosecond, so we can also look at changes on that time scale. It does not require contacts because the pulse is freely propagating. And I will show you, it also allows you to determine charge carrier density and charge carrier mobility in a quantitative fashion in a relatively straightforward way. And so this is the simplest experiment that one can do with terahertz on graphene. So we use what is called CVD grown graphene. So it's chemical vapor deposition grown. It's where you grow the graphene on a copper substrate, and then you dissolve the copper afterwards, and you transfer the graphene to a substrate that is typically just glass. And so the simplest experiment, and I'm very ashamed that this is really as good as my PowerPoint animations are going to get. So please bear with me. So here's the terahertz pulse that is hitting the bare substrate, and there's no interaction with the substrate. But if I run the movie again, you can see in this case there are carriers. Those carriers are accelerated by the field, and in that process the field loses some of its intensity. So some of the power that is, or the intensity that is in this pulse, is now transferred to the system and is dissipated as heat. And so the quantitative nature of this technique is that the change in the amplitude is a direct measure for the number density and the mobility. So it's the product of the number density and the mobility. And the phase shift that you see here, so there's a time lag between the two, which is proportional. This is the imaginary conductivity. So this is the amplitude is the real part of the conductivity. This phase shift is the imaginary conductivity, which is none other than the polarizability. So the difference in refractive index, because there is some real conductivity. So the underlying physical picture beneath this measurement is actually quite simple. So the terahertz field accelerates these charge carriers, the electrons or the holes in the graphene, and so thereby the field induces a current in the material. And so that current, we know any current will emit or can emit a field, and the emitted terahertz field is proportional to the time derivative of that current. And so we'll have an incident field that is transmitted, and then an emitted terahertz field that originates from that current, and those two will interfere. And so we have a total terahertz field, which is the sum of those two. And so we can backtrack from this black curve here, and comparing it to the blue curve, we can infer this red curve. And this red curve is what tells us how the field induced the current. So we can backtrack the current, the time-dependent current, from that trace here, and that tells us, of course, about the mobility and the number density. So that is the physical idea behind the measurement. And so we can analyze that in a little more detail by taking the ratio of those, or the difference of those two, actually the normalized difference, and Fourier transforming it. And so then we can really determine the real conductivity and the imaginary conductivity as a function of frequency. So it's clear that if you have such a single cycle pulse, it is a very wide pulse, so to speak. It has to contain a lot of frequency components. And indeed, the bandwidth of this pulse is about a terahertz, and it's very similar to its central frequency, which is also about a terahertz. So we have this rather large range of frequency over which we can determine the frequency dependent real and imaginary conductivity. And the lines that you see here, this black line and the red line, are a fit description of the data using the Drude model. And the Drude model is a standard textbook model of electrons that move around in a material, and they scatter every now and then, and that every now and then is determined by this tau r, the scattering time, and due to phonons or defects or other charge carriers. And you see that this simple model describes the data remarkably well, with actually only one free parameter, which is the scattering time. So the density of the charge carriers, which determines this plasma frequency, this we can obtain independently from Raman measurements. And so,
Mischa?
yes.
So what is the time resolution in your detection? Because you were showing in your previous slide that basically to separate the real and imaginary parts, you need some kind of a phase information. You'd indicated that you have your delta t, and so I'm wondering how well can you actually record? How do you record this?
Yeah, it's very good. Yes, it's an excellent question. So let me go quickly. Let's see here. So what we measure, in fact, is really the electric field as a function of time, where we make use of the electro-optic effect. So we have an electro-optic crystal, and if you apply a field to that crystal, it will rotate the polarization of the light that is transmitted through that crystal. And so we measure the quasi-instantaneous fields on that crystal by the terahertz pulse using the rotation of an ultra-short, so a 30 femtosecond 800 nanometer pulse. So we basically sample for each delay here the instantaneous field strength. And so the time resolution with which we can determine this this transient is much better, in fact, than the width of the transient.
Okay, great, thank you.
And we can actually see time shifts because we can measure small differential signals down to hundreds of attoseconds. So we're very sensitive to small phase shifts. But that's maybe a different story.
Great, thank you.
All right, so let me try to continue. And so this is just to illustrate that sort of the strength of this technique for characterizing charge carriers. So you have to realize that this is not a large density, right? It's 10 to the 12th per square centimeter. It's not a large density of charge carriers in the material. They are the charge carriers that are there are very conductive. So they have a very long mean free path or a long scattering time. But it's only one layer of material that we're looking at. And so we clearly have the sensitivity to characterize that one single conducting layer quite nicely. So I need to take you on a small intermezzo, which is what happens when we photo-excite graphene. And so what happens to this carrier distribution, what happens to the scattering time, what happens to the plasma frequency, to the number of charge carriers when we excite graphene. And this is now a little bit of an advance, but please bear with me. And so the thing that happens, of course, is that we will transfer charge carriers into, say, from what one could arguably call the conduction, the valence band into the conduction band of the material. They will scatter very quickly, and they will very quickly heat up. And so we now do a different kind of experiment. So we photo-excite the graphene here, we photo-excite the carriers, and the reference measurement is now the transmission of the terahertz through the unexcited graphene. And again, here's my not so great skills of animation in PowerPoint. You will see that there is a difference, or we find that there's a difference in the transmission. So we see that we have more transmission through the optically excited graphene. And that increase in transmission corresponds to a negative photoconductivity. So that means that we had initially in our sample a photoconductivity here and here that was equal, and somehow the optical excitation has reduced the conductivity in this case here. And so the spectrum looks like this. The spectrum is actually not very informative, but we can understand this reduction in the conductivity quite nicely when we understand that the excited electrons will kind of cool down through this direct cone here, and it will do so by scattering with other electrons that are present in this direct cone. And what that means is that the Fermi Dirac distribution of carriers will essentially heat up, and as with also conventional semiconductors, what happens is that the hot electron population has a lower conductivity than the cold electron distribution. And so in that sense, the graphene really behaves like a metal that when you heat it up, it is less conductive. And so this sounds a posteriori very trivial, but at the time that we found it, it wasn't. So the question that I now have is, so if this electron heating that we can induce with optical pulses, if that also happens when we do the experiment with terahertz pulses, where you could imagine, I mean, a very extreme case is where we have some multi-photon terahertz excitation and we achieve the same state here. But one could also imagine that we simply heat up the electrons with the terahertz pulse. And would that also reduce the conductivity and the mobility of the samples of the graphene? And this is not a completely academic question, because there's a large community of people that are trying to make ultra-fast graphene transistors. And so this is a plot of the transistor cutoff frequency. And so going up here, a higher frequency is a better transistor. And a better transistor also means a smaller transistor. So the gate length decreases. And you can see here the trend that has been going in this upper left. So this is the desirable region of this graph. The trend that has been going to the upper left for different types of transistors. But interestingly, if we look at the graphene based transistors, they sort of got stuck at 400 gigahertz. And this was in 2013. So this is, since then, there has not been a faster graphene-based field effect transistor. And so you might think, well, you know, you just showed me that this is such a fantastic material, you know, it's so conductive, only a monolayer, so it should be ideal for making field effect transistors. So is there some intrinsic limitation why you cannot go beyond this 400 gigahertz? And I will show you that indeed there is a problem with graphene that is intrinsic to graphene that we can't really overcome, and that is limiting the device performance, at least in terms of field effect transistors. So this is still the current world record. This was the world record in 2013.
Sorry, can I ask a question? So when you talk about the transistor performance, This is a real device that has been made,
Yes,
or are you
yes.
talking about the intrinsic
No,
kind
this
of
is a
speed
real
of the,
device. This is a
so
real
including the
device. Yeah,
leads and
yeah, yeah.
everything that goes with it?
Right.
Okay.
All right. So the question is, why haven't we been, so this is actually the sequence follows this trend here in time, but somehow it has stopped here. And the question is why? What is going on? Now you have to realize that if you want to, so for this 400 gigahertz graphene based transistor, you have a gate length of about 100 nanometers. You have a voltage over the channel, of typically a volt. It can be half a volt, it can be 2 volt, but it means you get up to field strengths of about 100 kilovolt per centimeter. And so in this case at 0.42 or 0.43 terahertz, so at roughly a terahertz frequency. And so this is something that we can look at, because 100 kilovolt per centimeter is a field strength that we can generate in our lab. It's not that difficult. And then we can see, is there some intrinsic problem with these high field strengths that become increasingly higher as you make the device smaller. And of course, the frequency also gets higher as you make the device smaller. And so the question is, how does graphene respond to, relatively strong, I think for most optical people, 100 kilovolt per centimeter is not very strong, but for terahertz and device people, it is quite strong. And so that is something, this is an experiment that we can very easily do. So this is the measurement that I showed you at low field strength. So here's the real conductivity and the imaginary conductivity. And I showed you that this is the scattering time. We can read that off the graph here. And so what we're going to do now is just do exactly this experiment, but now with a terahertz pulse that increases in field strength.
Mischa?
Yes?
Could you go back one slide? In fact, there was a question earlier that I missed.
Okay.
Sylvia wanted to know what she detects some oscillations here, and the symbols do oscillate around dance around the things in an oscillatory way in the black and the red. Could you say what that is? That just a systematic, or?
I think that is coincidence. So there is, Kramer's Kronig, of course, tells you that if one of the two oscillates, the other one oscillates as well. So they are correlated. But this is just noise that you see here. The only thing that could be is that because we Fourier transform this waveform, if we have some AC offset, that sometimes introduces some correlated noise, but I don't think that's the case here.
Okay.
Okay, so we're going to do the experiment that I told you about. So we're just going to transmit this terahertz pulse through the doped graphene and look what happens as it comes out. And we're going to change the terahertz field strength from a few to a few hundred kilovolt per centimeter. So again, this is the low field result that I showed you already. And now I show you the same trace, but now to avoid a very busy graph, I've separated the real from the imaginary conductivity. And so here you can see at a few kilovolt per centimeter, we have this Drude-like conductivity with a scattering time of about 140 femtoseconds. Now, as we increase the field strength, even as it goes up to a few tenths of kilovolt per centimeter, you see that the real conductivity drops pretty dramatically. So the imaginary conductivity does not drop as quickly, but this is all consistent. But the most important thing is that at, say, 40 kilovolt per centimeter, you can see that the conductivity at a say a terahertz, which would be a typical operating frequency, it has dropped by a factor of 3 already. So the interesting thing is that we can still describe all these traces using the Drude model. And here's you see the drop of the conductivity. This is now at 1 terahertz as a function of field strength. So you see that already at the lowest field strengths, there is a dependence. And so that is the same thing that we observed in the, this is how we interpret it, at least in the optical excitation experiment. So it's simply, we're heating the electrons with our terahertz pulse. Those hot electrons have a reduced conductivity, and that is what we're seeing here. Now, if we go to even higher field strength, so up to 100 kilovolt per centimeter, which is actually typical for the device, you can see that at that point, the conductivity at 1 terahertz is gone. I mean, it's 0. And we cannot describe these measurements anymore with this simple Drude model. So there's a breakdown of the Drude model, which may also not be completely surprising because we enter a very hot electron distribution state. But this explains why the device, the graphene-based devices are limited to a few hundred gigahertz, because there, when you apply these fields, you still have some conductivity. But if you go to even smaller gate lengths, higher fields, higher frequencies, the conductivity really dies. So now there's one thing that I'd like to point out here, which will be interesting. So we did not at all understand it at the time, but you can see here that at high frequency, it looks like we're having a negative real conductivity, which actually corresponds to that there would be gain in the system. So there's more terahertz intensity coming out of the sample than going in. And I will show you that this is actually real later. But at the time, we just didn't understand it. So we thought it must have to do with, we must be making some systematic mistake. So the lines that you see here are not Drude fits, but they are the results of a very simple calculation where we know the absorption of the graphene. So the graphene absorbs a small fraction, typically a few percent of the terahertz pulse. That although it's relatively small amount of heat, we're not injecting any carriers, so the carrier density remains constant. Although this amount of heat is very small, we're not even having microjoule terahertz pulses. These are really nanojoule terahertz pulses. But the heat capacity of the electronic heat bath is so small that we can actually get a substantial heating of the electrons in the graphene. And so what happens is that you can explain these what seems to be rather intricate electrodynamics by simple thermodynamics, and it's really simply the temperature of the electrons that determine the response of the sample. And so that the temperature increases during the terahertz pulse, and we can account for all of that. And we find that we can reach temperatures of up to 1,000 or a few thousand Kelvin in our these are simple tabletop experiments. So there's a limit to ultrafast graphene transistors, which is really determined by an intrinsic property of the graphene. And so the terahertz field that you need to operate an FET actually kills the conductivity due to the heating of carriers. So it's not that the whole device overheats, but it's simply that the carriers, the electrons get very hot, and those hot electrons are not actually conductive anymore at those high frequencies.
So, Mischa, what does that mean? I mean, if you were to do Raman spectroscopy, would you actually see that the bonds are more active, or when you say that the whole thing is not hotter, what does that mean exactly?
So it means that the device is not hot in the sense that you're not heating up the phonon subsystem substantially. And so this reduced conductivity really is due to a separation of timescales between the ability to heat the electronic heat bath in graphene with a short pulse and the relatively slow electron phonon coupling, which then thermalizes the whole system and actually effectively brings it back to this state here. So within a few picoseconds after you have this hot state, it cools down. But you will reach a steady state in a device that where you keep heating up the electrons and they will have a reduced conductivity.
Mm-hmm. But that means that, so the fact that the electrons are hot, I guess the picture you have is some kind of a collisional situation where the electrons are not just ballistically moving, but they're bouncing into each other, and then
Exactly.
there must be some kind of a heat transfer to the matrix, or not?
Yes. So, but that it takes longer. I will actually get to that. So we're going to we're going to use this. Yeah, no. It's a very good point. So we're going to use this, in fact, in what follows. So to summarize what I've told you so far, so graphene has a couple of great electronic properties. It has very high mobility. It has very high photon to electron conversion, which is actually also tunable, we showed. But high fields are a bit of a problem because of this heating effect. And so what I'm going to tell you now is that it's, you might think it's a bug, and we actually had a lot of problem getting that paper published because people didn't like it. And it is a bug, of course. I mean, it is a problem, but you can also use it. And that's what I'm going to show you next. So during my introduction, I've told you that this electric field of the terahertz, it drives a current, and that current emits a field again. But I've shown you that if we increase the field strength, even moderately, this same electric field will also change the current because it changes the conductivity. Okay, if you lost me here, you have to speak up now, because this is kind of a critical point. All right, then I'll continue. We know that the current emits right, the terahertz field. And so what these two things combined mean is that the emitted field responds very nonlinearly to the incident field. So if we increase the incident field strength, we change the nature of the response in a nonlinear way because the field heats the carriers, and that changes the current because it changes the conductivity. And so that means that this is a highly nonlinear optical material in the terahertz range. And so we should be able to do nonlinear optics with graphene. And that's going to be the second part of my talk, is about using this heating to do nonlinear optics with graphene. And so here is an illustration of how nonlinear really it is. So this is a terahertz pump, terahertz probe measurement. And so again, you have to keep in mind, this is one monolayer of material, and you can change the conductivity or the absorptivity of that material by almost 10% with a fairly moderate field. And so here you see that the conductivity drops dramatically. This is averaged over the whole terahertz spectrum by 10%, and it recovers again within a few picoseconds. And you also see that it goes back to roughly the original state it had before the pump pulse, the terahertz pump pulse hit the sample. And so what that means is that we start with a cold, right, room temperature Fermi-Dirac distribution of carriers in the system. We heat it within a few hundred femtoseconds, so that it's limited by the pulse duration of our terahertz pulse, right, which is 1 or 2 picoseconds. And then it takes a few picoseconds to cool again and to go back to this cold state, right? This is an important picture to have. So we start off with a conducting material. We apply a moderate field for a very short time. It kills the conductivity, but the conductivity recovers on the time scale of a few picoseconds. All right. Okay. So the experiments that I'm going to show you now are free electron laser based, where we can use a multi-cycle pulse, so not a single cycle pulse, but a pulse that has a better defined frequency. It has a narrower bandwidth. And we're going to, again, use our simple CVD grown graphene samples. So these samples are really straightforward. And the idea of using graphene as a nonlinear optical material is that we come in with this oscillating field, and this field is going to drive a current, which is going to emit the terahertz field. But if the response of the current to the field is sufficiently nonlinear, we should be able to see the third harmonic of the fundamental that comes in. And so the idea is conceptually very simple. So we come in with this oscillating field, and so we have field strengths of tens of kilovolts per centimeter at the peaks here. And so initially the electron distribution is cold. Then as the field switches on, it starts to heat the electron distribution, but then the field is off again for a while. And during this period of low field strength, the system can cool down again. And then we again go to a very hot state as the field ramps up again. And as the field switches off again, we go again to a cold state. And so we go into this cycle, this heat and cooling cycle with every oscillation of the field. And so if the field oscillates slowly enough, and we used a 0.3 terahertz frequency to do this, we will just go into these hot, cold, hot, cold, hot, cold, these cycles, and this will bring this nonlinear current that we need to see the higher harmonics. Okay, is this clear to everybody? Then I will continue. So yeah, here a lot of hots and colds here. Sorry, a little bit overdid it a little bit. So this is the idea, and I'll show you that we can not only get the third harmonic, but we can get the fifth harmonic. We've even seen the ninth harmonic, and you can actually see it pretty much from the raw data. So the black line here is the incident field, actually going through the substrate, the bare substrate. The red line is the field. So this is, again, this electro-optic sampling is the field going through the graphene on the substrate, where we have filtered out the fundamental by a factor of 10 to the 2. And if we take the difference between those two, you can see the blue line here, and you can actually see the harmonic oscillations on the fundamental oscillations in the field. And again, these are not very high field strength. So these are field strengths of tens of kilovolts per centimeters. And so the remarkable thing is that we get about 1% conversion in terms of field. So that's 10 to the minus 4 conversion in terms of intensity with a 10 microjoule pulse. So the nice things about these free electron lasers is that you can get a lot more pulse energy. And so here's a spectrum of the incident field on a log scale. So I told you we were at about 0.3 terahertz with the fundamental. This is what the spectrum looks like. And this is, oops, something went terribly wrong here. Let me see if I can, no. Sorry, I need to correct this. I don't know why this, what happened here. I would like to be able to show you the whole thing. So this should do the trick. So here you see again the fundamental, and superimposed on that you see the third, the fifth, and the seventh harmonic, which are well above the noise level of the experiment. So very high, very efficient harmonic generation. And again, I'd like to stress this is room temperature, 300 Kelvin. It's modest field strength, 85 kilovolt per centimeter, and again a kind of a 1% field conversion efficiency. So 1% for the third harmonic, 0.1% for the fifth, and another factor of 10 for the seventh harmonic. And so if you compare the fields that we need to generate higher harmonics, it's tens of kilovolt per centimeter, to the typical high harmonic generation that you need from Bloch oscillations, that's several orders of magnitude higher. So this is the effective nonlinear susceptibility of this material is immense. So here you see a filtered version of the third, the fifth, and the seventh. So we Fourier filtered and windowed the traces that we measured to highlight the different harmonics. And so we can again use our simple model because we now know how, when we heat the electrons, how the conductivity changes and how rapidly it cools. We've measured that independently. And so that simple model actually reproduces the data quite well. I mean, there's a couple of details that we miss. So one of those details is that for the seventh harmonic, there's a clear delay between the maximum in the fundamental and in the seventh harmonic, which we don't see in the calculation. But I think by and large, given that we're not theorists, this is a very simple thermodynamic model. It works remarkably well. And so that is also true if we calculate the spectrum with our model. We capture the relative intensities of the different harmonics fairly well, I would say. So how is it possible that we have this incredibly large third order nonlinear susceptibility, or this effective susceptibility with this material? And the reason for that is actually very simple. So what we make use of is the extremely large polarizability of the free electron. So we're literally driving the free electrons over mesoscopic, over hundreds of nanometers length scale through the material, and thereby we create a huge polarizability, which, if you look at normal, say a BBO crystal, where you do second harmonic generation, what you use there is the polarizability of bound electrons and not free electrons. And so you can, those are very polarizable materials, but they're surely not as polarizable as a gas of free electrons. And so this is the physics of why the nonlinear susceptibility in this material is so incredibly large. And so coming back to our original measurements, this explains the gain that we have here, because our spectrum in these experiments actually peak at about 0.6 terahertz. So the spectrum kind of looks like this. It tails off to higher frequency. And so we now understand that we were generating the second harmonic of this 0.6 terahertz, and we're depleting this spectral region here and making, with some degree, these are very high field strength, with some degree of efficiency, these higher harmonics that you see here show up at around 1.2 terahertz. So there is indeed, this is the actual spectrum. So there is indeed some gain. So what I've shown you is that we can very efficiently generate higher harmonics using a single layer of graphene at room temperature. This is enabled by this very high polarizability of the free electrons, and the nonlinear optical coefficients are stellar. I mean, they're unprecedented. So, where do we go from here? Well, so can we boost this harmonics generation? Well, there's a few things that are kind of apparent. You could think of making multi-layer structures, which should certainly work, but more interesting and two avenues that we've pursued recently is to tune the Fermi level of graphene. So if there's more electrons, we can induce a higher nonlinear current response to the driving field. And the other thing is we could increase, using metamaterials, the incident local terahertz field strength, and thereby increase the efficiency of the process, or rather allow the use of weaker fields. And so one can tune the Fermi level in graphene, so using this type of gated device. It's actually...
So, Mischa,
yeah.
There is a question basically asking whether whether you've investigated the different substrates. So you're talking now about changing your Fermi level, and
Right.
in the beginning you explained that the substrate actually makes the whole thing conductive. So that must then depend a lot on the way you put the thing on the substrate.
Yeah.
Is that right?
That is a very good point, and this is also part of the reason why we wanted to use this gated device, because as you can see here, depending on the gate voltage, you can change the resistance, and so the doping. So you can go from P-type to N-type doping. So this is the N-typed dope branch. This is the P-type dope branch, and you can indeed do the same. Achieve the same using different substrate, but here you literally have a knob right here where you can just change the gate voltage, and you can tune the Fermi level. So it's a very good question, and we address that question using such a device here. And then, maybe not too surprising, you see indeed that if you apply a higher gate voltage, so you dope the graphene more, you get more efficient high harmonics generation. So it's a little bit small, but the dark blue here is the largest gate voltage, so 560 millivolts. And so here you see the efficiency of the third, the fifth, and the seventh harmonic as a function of gate voltage. And you can see that indeed we can go up, say, an order of magnitude in the third harmonic by more efficiently doping the graphene. So it works. It actually only, you also see that it levels off because at some point the amount of electrons also starts limiting the nonlinearity. So you can't heat up the electron bath so much if you have more carriers that you have to heat up. So there is a limitation to how far you can push this. So the second thing was to use a terahertz meta material, and this was a very simple experiment where we compared putting gold stripes on graphene with no gold stripes on graphene, and then using a spatial filter. And then you can see that this is for actually very low field strengths. So this is about 20 volt per centimeter. And here you see again the third harmonic. This is at somewhat higher frequency. And for pure bare graphene, it's barely above the noise, but for the metamaterial, you can see that it's, you know, over an order of magnitude above the noise. And so this is a nice way of using the graphene nonlinearity with tabletop, very simple laser systems. And so you can see that at very low field strength, you can get an enhancement of up to, you know, a factor of 40 compared to the bare graphene. So with that, I'd like to conclude, and I hope I've shown you that hot electrons in graphene have exhibited a reduced conductivity, which is good and bad. I mean, it's bad in the sense that it's going to be very difficult to make a very fast, small field effect transistor using graphene. It's good in the sense that you very quickly reach a nonlinear regime where you can then use the nonlinear currents to generate high harmonics extremely efficiently. And so with that, I would like to end and thank you for your attention. So this is a cartoon of a terahertz pulse hitting the graphene, and then all these wonderful colors come off that of course we can't see, but I hope you like the pretty picture. So thank you very much for having me and for listening to me for such a long time.
Well, thank you very much, Mischa. I applaud on behalf of the whole institute. Yeah, this is interesting from all kinds of different points of view. And there were some questions, and there are already other questions that are trickling in. So maybe we try to go through them.
Yeah, so I can
together.
see them now.
Okay.
So Sylvia, we had, I think.
I think we're down to
Randir.
Question. Randir we had as well, basically.
Oh, yeah, yeah.
And so now I think the next question is regarding your slide 53. Can the gate voltage be replaced with another perpendicular terahertz field to affect the Fermi level?
That is a very good question, and it will take me a very long time to answer that question.
Yes, no.
So the very short answer is no. The longer answer is that it is a good question because when the Fermi, actually what is constant is, no, I think that let's just stick to the short version of the answer. And that is no. So you can change the electron distribution with a terahertz pulse, but not the Fermi energy to a first approximation.
But I won't get into that. But I mean,
so
the temporal part makes a difference, right? I mean,
yes, yes, and the approximation is that actually the chemical potential is conserved and not the, and so the Fermi level actually shifts when you heat it up. So it's subtle. Okay.
So the next question from Johannes is about the more technical things like the types of detectors and light sources that you're using. What goes into a real experiment? You said already it's tabletop.
Yeah. So it's,
maybe you can.
Yes. A completely standard terahertz experiment that we do has a kilohertz amplified laser system, but it can be any system, but it helps because we do optical excitations or want to generate high fields. We prefer to have a kilohertz system. And the optics are really simple. So we start with 800 nanometers, and then the terahertz generation is just putting a zinc telluride crystal in the 800 nanometer beam. And the only thing you have to be aware of is that you don't fry the zinc telluride crystal, but otherwise you can increase the power. And then we generate the terahertz using this process called optical rectification, which is essentially difference frequency generation within the bandwidth of our 800 nanometer pulse. And so it's after that you have a coherent terahertz beam that you can then manipulate, and we read it out with this electro-optic sampling where we have a delay line, and we delay a 30 femtosecond 800 nanometer pulse to sample the quasi-instantaneous field strength within this terahertz pulse. So it is really, we do all sorts of experiments in our lab, and this is really the simplest. It's not difficult.
Okay. Yeah, so the next question, can you phase match the process of, I have to say, I'm not sure exactly what
high harmonic generation.
Okay. Yeah, I think that was
maybe Gabriel is Spanish, right?
Yeah. Okay, so higher harmonic generation by increasing the length of the material, multiple layers of graphene, or via shaping the terahertz pulse?
Yeah, this is also a very good question. So yes, so increasing the length of the material, or maybe equivalently using multiple layers of graphene, is actually difficult because the properties, the electronic properties of a single layer graphene are different from a bilayer graphene, or different from a tri-layer graphene. So you would have to somehow isolate those layers from one another. And if you make sure that that separation doesn't affect, that there's no pulse propagation problems that affect the phase matching of the process, that should be possible to do. It's not something we tried, but you could imagine that you put a graphene layer on glass, then you somehow put a thin layer of glass on top of that, and then you put another graphene layer on top, and you make a sandwich. That would work. Shaping the terahertz pulses, we haven't tried. That's an interesting thought. I would have to think about that some more. Yeah.
All right. The next question, have you considered studying the changes in superconductivity of different organic molecules or twisted bilayers of graphene and such?
We personally don't do that, but there are certainly groups that use terahertz conductivity measurements on superconductors, and that is also very exciting field. Twisted bilayers of graphene is also a very interesting field indeed. The problem, or I think one of the drawbacks of terahertz, is that because the wavelength is so long, right? It's a sort of 300 micron or 100 micron wavelength. You cannot focus it very tightly. So for these 2D materials, you really need extended. So if you're thinking about twisted bilayers, the correlation length of that twist is usually a lot shorter than 100 microns. And so that makes it difficult to use terahertz on those complex materials.
Okay, there's one more question. If it's possible to engineer the nonlinearity efficiency by manipulating the phonon densities of states in the substrate or the size of the substrate and such?
Yeah, that is a very interesting question. And so let me just go back very quickly to this scheme here, right, where we have this cycle of heating and cooling, and that is indeed, especially this cooling step is determined, the rate of that is determined by the electron phonon interaction. And indeed, you can manipulate that to some extent. We've actually spent a lot of time trying to do that, and we only gain sort of a factor of 2. It's not the order of magnitude effect that one might have hoped for. So you can indeed manipulate the electron phonon coupling and actually also through the phonon density of states and enhance the effect, but it's very limited. And the size of the substrate doesn't matter, because it's really the electron phonon coupling within the graphene layer. So the transfer of heat from graphene to the substrate is even slower.
So you showed at the end that you were using a kind of a simple metamaterial to get higher fields and all of that. There is a question that is maybe related to the previous question and that part, in the sense of asking whether you can shape your graphene flake to get more of an antenna functionality. You just said that the size doesn't matter, but still, if you were to somehow do it in a way that you have some kind of a cavity or antenna type of effect, would that?
I don't have a quick and intelligent answer to that. I mean, so this goes into sort of graphene plasmonics, right?
I guess, yeah.
Yeah, and then that works. The question would then be, how do you how would you couple out the light? But that, I mean,
yeah, I mean, these things are usually quite lossy, so they have a certain kind of mode, but a lot of it still comes out. But you're right. I mean, you would have to engineer the input output and
yeah,
to get the most out of it.
but it's an interesting question, Andre. So I don't have a clear answer to that. I think I'd have to think about it.
Okay. I don't see any other question right now. So can maybe just a kind of an out of interest, what gets you guys interested in graphene? How does that tie into the other type of research that is done in your group? Do you see a kind of a bigger picture there, or is it just a fun thing to do?
It's actually both. So we also look at, we've used graphene as an electrochemical electrode in water electrochemistry. And there we also use terahertz to look at processes going on at such an electrode. In part, it was also simply due to Klaus Mühlen, who's this carbon emperor in Germany, who was he's still at our institute, but he's retired now officially. Yeah. And he makes all these really neat carbon nanostructures, so carbon nanoribbons of, atomically controlled width. And so that is what got us into graphene and graphene nanoribbons. And then we saw so many interesting phenomena in the graphene that we essentially got sucked into it.
Okay. So I think there's still no further question. On behalf of everyone, I would like to thank you again for taking the time to talk to us and tell us something that has lots of different aspects that are interesting in Erlangen, you know, 2D materials, laser spectroscopy, and fast electronics and all of that. It was a lot of fun. Thanks very much, Mischa.
Thank you. Thank you. Thanks
And
for
I have to
having me,
again
and thanks for
applaud on
listening.
behalf of everyone. Yeah, you would have by judging by the numbers, you would have completely filled our auditorium, and we're longing to see that auditorium filled again, but maybe in some other time. Okay, so I close the session. We have some other kind of breakout sessions afterwards.
All right. Thank you all for listening to me. Appreciate it.